Hey, today we're going to talk about length contraction. Key idea here is if something is moving fast relative to you, approaching the speed of light, it will appear shrunk, like compressed in its direction of movement. So if I could sprint really close to the speed of light and you guys were all watching me, you wouldn't notice any of the COVID weight. It'd be all good. Anyway, so here's our formula. So the length you perceive, let's say you got a car. You're driving this car and it's, I don't know, 3 meters long. And if you're driving in the car, it's 3 meters long. From your perspective, you're moving with it. It seems perfectly normal to you. People watching you go really fast, if you could approach the speed of light, would see it as, say, maybe 1 meter long. So it would appear shrunk in the direction of motion. All other directions are unaffected. It's just the direction of direction of motion. So if I was running really relative to you, I'd look thinner in a weird way, weirdly compressed. But my height would be the same and all that. So here's our formula. One thing I wanted to mention last time is kind of what happens when your velocity approaches the speed of light with time dilation. Now, if this approaches c, you have 1 minus c squared over c squared, which is 0. So basically, regardless of the time apparently passing for the person going the speed, it'll appear infinite time is passing for everyone else. So the kind of takeaway from this is if someone is traveling away from you at the speed of light across the universe, time will appear to stop for them. So time will stop for them, but from the perspective of the person inside the spaceship, traveling at the speed of light, it would appear that, so this is how long they would perceive the universe. This would be the original length of the universe, possibly infinite, but let's say like observable universe, something measurable. And then this, if v is, from the perspective of the person in the spaceship, the universe is moving away from them at the speed of light, or traveling at the speed of light. And therefore, if you've got 1 minus c squared over c squared, it would get multiplied by 0. So regardless of the original length of whatever section of the universe, from the perspective of the pilot of the spacecraft moving so fast, it would appear that the universe would compress to 0 like length. So time would seem to be normal for them, but the universe just shrank to the point where it has no width in the direction of their motion, and they just traveled it instantly because it has no width. From everyone else's perspective, it's like time is stopped for the person. So I always thought that was pretty interesting. All right, let's try a couple examples. Oh, by the way, another thing I love about this, one of my favorite things, I love Velocity Raptor just because all of this stuff is not intuitive. We never run into relativistic effects well, we do all the time. I mean, electromagnetism, GPS, all that stuff relies heavily on relativity, but it's not so much in our everyday experience, in our intuition. Velocity Raptor helps you with that. And one of my favorite things in that is those gates where, like, from one perspective, one of the doors opens at the same time the other door closes, and it'll like squish you unless you get going really fast. And the reason for that is from the gate's perspective, you've just shrunk a bunch. So from its perspective, your length is short enough that you can fit between it. Well, one sort of opens and the other closes at the same time. So you fit, you are shrunk. From its perspective, it's great. from your perspective, moving really fast, it appears that things that were separated in space, like before you thought the two events were identical in time, they're simultaneous events, and were just separated in space, but once you get moving, your perspective shifts, so the two events are separated in time as well as space. So there is a gap between one of them opening and the other closing. So again, that's the idea that comes better with Minkowski diagrams. The reason that all this crazy stuff happens is because space and time are interlinked, and different people's perspectives on when things are happening and where they're happening get muddled. It depends on your perspective, whether things are separated in time, separated in space, or separated in some mixture of the two. So space-time, it's craziness, very not intuitive. Play lots of Velocity Raptor and think a lot. Right. So first question I want to go over with you guys, I'm going to go over questions 3 and 4 because they seem to be the most interesting. By the way, light years is if you didn't know, it's a measure of distance. It is the distance light travels in a year, and it's pretty darn far. So we've got a distant star is 6.25 light years away. How fast would a space vehicle need to travel? So this distance would appear to be 2.85 light years for an astronaut on the space vehicle. So they're moving really fast, so space seems compressed in their direction of motion. They feel like they're at rest, the universe is moving, so the whole universe will appear compressed to them in their direction of motion. If it's 6.25 for us at rest relative to the universe, maybe, times the square root of 1 minus v squared over c squared is going to equal 2.85. And notice how before when we solved for v squared, it ended up looking kind of like this with v and c for the time dilation for that question we did. Now it'll flip a bit. So let's solve. We'll kick this guy down there and then square both sides. So we'll have 2.85 all over 6.25. We will square both sides. So all this gets squared, and that will equal 1 minus v squared over c squared. We will subtract this guy from both sides and add this guy to both sides. So we'll have v squared over c squared equals 1 minus 2.85 over 6.25. Maybe I'll just have them both squared. Same thing as squaring the whole thing. And then I will multiply both sides by c squared and then square root the whole thing. So we will end up with v equals the square root, or I guess c square root 1 minus 2.85 squared all over 6.25 squared. And again, we can make this into a form where it will always work. So if you ever want to solve for velocity and you're doing it based on length contraction, your v equals c root 1 minus L over L naught. With them both squared, of course. So yeah, whatever this happens to be, check your answer key if you're looking for the actual number, but here's the gist and a little handy version of the formula if you need. Notice it makes sense. If the lengths are both the same, like if the perceived length from someone not moving with the object and the perceived length of the person moving with the object are the same, you'd have 1 minus length squared over length squared, which would be 1. 1 minus 1 is 0, and 0 times anything is 0. So your velocity would be 0. All right. For the next guy, last guy we're going to do, I'll try and do it quick. I got it started. So your key idea with this one, the reason I did it is because it's got this brick wall that's 90 meters long and 14 meters high. So again, things only have their length changed in the direction of motion. So it looks like they're traveling parallel to this brick wall, so along the length, I presume. So the height will not change. It will stay at 14. So that's your height. But this distance will change. So from the person traveling really fast, they will see the world and all the universe in that direction as being compressed. So their length they perceive the wall to be will equal its length if you're at rest to it times the square root of 1 minus 0.8 c squared over c squared. Notice our c squareds cancel. 0.8 squared is 0.64. 1 minus 0.64 is 0.36. And the square root of 0.36 is just 0.6. So 90 times 0.6, you would end up with 54, I believe. So I believe, double check the answer key, but I believe it would be 54 meters. And that is enough for today. Thanks for listening, and keep up the great work.